All right, let's get going. So I think this is good. All right. Today we're going to be talking further about polynomial functions and models. Specifically, today we're going to be looking mostly at their graphs again. This is chapter 4.2 in your book. We're skipping a little bit of the stuff that's in there. Some of it wasn't particularly important. I'm talking about concavity and stuff, which, whatever. Um, I'm not gonna put it on your test, and there's 8 sections in this, so we're gonna not bother with that stuff. But the things we are going to talk about in this chapter, we're going to start with interpreting polynomial graphs. So we've already, this is kind of in the way. Let me see if I can get rid of this. Okay. We've already talked about a few of the key, or the major key points in graphs. You should already know about x-intercepts and y-intercepts. In the last section, we discussed minima and maxima. If you remember from quadratics, we also talked about the vertex. That was just a particular kind of minima or maximum. It was the only one that a quadratic is ever going to have. And today we'll be talking about a few key things, primarily turning points and end behaviors. You should also know about degrees, but degree doesn't really show up in the graph directly, so we'll talk about that in a little bit too. So starting with turning points. Let me see, my face feels really in the way everywhere here. Try bottom right. Starting with turning points. So the turning points of a graph occur whenever the function goes from increasing to decreasing or from decreasing to increasing. You'll notice that this is the same as what we said yesterday for minima and maxima, specifically the local ones. Obviously, the absolute maximum and absolute minimums can be different, but the local minimum and maximum occur anytime a turning point occurs. And these are some of the most important points in graphs, especially when modeling real life data. We'll look at some examples of that in a little bit, but for instance, let me see if this, there we go. So in the first graph over here, this one, obviously it doesn't have any turning points. It's the same all the way through. This is the same way. There's no turning points here. This is a quadratic function. It has one turning point. It's the vertex right there. It's also the absolute minimum in this case. This one has a maximum or a maxima right here and a minima right there. These are both turning points, so this graph has 2 turning points. This one has 1, 2, and 3 turning points. This one has 1, 2, 3, and 4 turning points. So the number of turning points is the same as the number of minima and maxima together. It's also probably worth noting that functions don't have to have their maximum number in each one. So like, for instance, this quartic function with a degree of 4 could be drawn, there could be a quartic function that only is going to have 2. So this doesn't necessarily tell you the degree of the function right away. But we'll talk more about that later as well. See, I don't think there's anything else to say about that one right now. Oh, when you're looking at actual graphs that have actual coordinates on them, you can estimate these points just by guessing approximately where this is and where it isn't. So obviously, if it's at like a point that's, you know, solidly on your grid lines, you can say like, oh, this is -1, 1. But a lot of the times, or you know, this one hits at like 4, 0, whatever, 0, 4. I can whatever. So sometimes those will be at really obvious points. Sometimes they won't. The book is going to have you estimate a few different points of them, and it's worth noting or knowing how to do that. But that's just looking to see about where it lies on the graph. So that shouldn't be too difficult. Here's an example of a real-world data interpretation. This is the graph of a projectile being thrown upwards. It's actually technically the theoretical graph of a projectile being thrown upwards. This doesn't account for air resistance at all, which isn't ideal, but doesn't really matter. The height is described by the y-axis and time is described by the x-axis. So over here we have height, right, as the ball is going up, or the projectile, whatever it is. I think this one was a baseball, but doesn't really matter. As the ball is going up, time is also going forward. So the question is, what does the turning point right here represent? And in this case, the answer is this is the maximum possible height that the ball hits, right? It's the maximum height. It is also the point where the ball stops going up and starts coming back down. This one's pretty obvious because of the shape of the graph. But we could also say something like if this was a guy running on a track, for instance, and this was his distance from like the starting line. So he starts running, he's running forward, he's getting further away, further away, further away, and he starts to turn, and he's a really slow turner apparently for some reason. So he takes this really wide, long, circle-y turn, hits the furthest possible point that he gets away from the starting line, and then he can come all the way back. And by the time he's back, he's running pretty much straight forward at maximum speed. So basically, you just know that a turning point always means that something is happening when it's modeling real life data. And it kind of depends on what data it's actually supposed to model. Number of turning points and degree of the function. So hopefully you remember that there's a relationship between the degree of a function and the number of minima and maxima a function can have. We talked about this yesterday. We said that the number of maxima or minima a graph could have is one less than its degree. So a quadratic function, which has the highest exponent of 2, can have 1 maxima or minima. An x cubed can have 2. X to the 4th can have 3. X to the 21st can have 20. X to the 3000th can have 2999. So it's just the number, the degree minus 1. Since minima and maxima are effectively the same thing as turning points, a turning point is both minima and maxima. Obviously, not all turning points are going to be minima, not all turning points are going to be maxima, but maxima and minima are both together form the group called turning points. So the same relationship applies there. The maximum number of turning points on a polynomial graph is equal to the degree of the function minus 1. So again, quadratic function with x squared, you would have 1 turning point maximum. For x cubed, you'd have 2. X to the 7th, you'd have 6 turning points maximum. And like I said earlier, it's not necessarily the case that they'll always have that many. For instance, if you just have the graph x to the 7th, this one is going to be decreasing when x is negative. It's going to look almost just like this. It's actually always going to be increasing. It's not going to have any maxima or minima. The maxima or minima come generally from adding in the other bits. So like usually what you'll get is like an x cubed minus x squared plus x plus 2. This will give you the maximum number of turning points most of the time. Okay, so here we just have a little bit of a test question about this. What is the maximum number of turning points in each given function? So this one, we just want to look for the degree first. This one has a degree of 3 because 3 is its highest exponent. 3 minus 1 equals 2. So we know this one is going to have 2 turning points maximum. This one, we've got 7x to the 8th plus 4x to the 7th minus 3x. We don't care about any of this stuff. We're just looking at the degree. The degree is 8, which means it's going to have 7 turning points maximum. This one, we have x to the 5th plus 2x to the 9th plus 6x to the 4th plus 3x. This one is a little bit tricky, or at least it's meant to be a little bit tricky because you might be tempted to just take the first one and say 5 minus 4 or 5 minus 1 is 4. But again, the degree is based on the highest possible exponent. So in this case, that's a 9, which means there are 8 turning points on this one. And then the last one, we have 3x to the 12th minus 4x. 12 is the degree, so the maximum number of turning points is 11. Right? If that seems super easy, that's because it is. If it seems super complicated, that means that I've been really unclear. All right, so turning points to degree. We can also run this process in reverse and solve for the minimum degree of a function based on the turning points in its graph. For example, if we have 4 turning points in a graph, we know that the degree of the function must be at least 5. It can be higher, so we don't necessarily know the full degree of the function, but we know what it must be at minimum. So for instance, graph number 1. This has 3 turning points. There's one here, there's one here, and there's one here. That means the minimum degree of this function is 4. For graph 2, we've got a turning point here, we've got a turning point here, we've got this weird straight line thing through here, but there's only one obvious region where it's going to change. So this one has 3, which means, again, the minimum degree must be 4. This graph right here has 1 turning point, 2 turning points, so its minimum degree must be 3. And this one is the same thing, 1 and 2, so its minimum degree must be 3. You could imagine having a graph that looks, something like this, where it's 1, 2, 3, 4, 5, 6. It goes like that. The minimum degree of this graph would be, there's 1, 2, 3, 4, 5, 6. The minimum degree of this graph would be 7. So again, that one shouldn't be too terribly difficult, I don't think. I skipped the question part. So the last thing we want to talk about today is end behavior of a graph. Specifically, when we're talking about end behavior, we're talking about what happens to the line as the graph goes this way. So the end behavior of a graph is also very important. Specifically, we're looking at the behavior of the graph as it moves to the right. I just said that. A polynomial graph will always end with the y value either heading to positive or negative infinity. And we can determine whether it's going to be going up or down by looking at the leading coefficient. So let's go back and let's look at these graphs right here. Assuming that these lines were continuous, they'd have arrows on all of them, but the website that I got these from as demos did not have arrows on all of them, which doesn't really matter, but point is, so we don't really care about anything that's happening on the left side of any of these graphs. That's not what we're talking about when we're talking about end behavior. You could also calculate that too. That just is a little bit more effort and it's not really worth it most of the time. What we're talking about is as the graph goes this way. Now, presumably you can see a situation in which we could have, x is 5,000 on each of these. And obviously this y number for this one, for instance, would be incredibly high, right? If x is, what is this, like 5 at 2.5, at 5,000, x or y would be some ridiculous number. So this one, the end behavior of this would be said to be positive because it's going up towards positive infinity. This one right here is going to be negative. It's going down towards negative infinity. And as we go further and further to x, the bigger x gets, the smaller y gets. That's the idea behind this end behavior thing. So why are we just looking at the leading coefficient? The way this works is actually if the graph is going down, a must be negative. If the graph is going up, so if it's positive, then a must be positive. And the reason for that will be explained here. Let's look at the function 1/10 x to the 5th minus 25 x to the 4th plus 3. So first of all, at incredibly small x values, actually really anything less than 1, the plus 3 right here is the most important thing in this function. Right? For instance, when x is 0, we have a 0 to the 5th, which is 0 times 1/10, 0. 0 to the 4th, 0 times 25, 0. So we have 0 minus 0 plus 3. So this 3 is the main determining factor when x is 0. But the bigger x gets, the more and more important this is going to get, even though this number seems bigger, right? We've got a 25 times x to the 4th, and that's going to be a lot more important in small values of x. For example, when x equals 2, f of x is negative 393.8. Now, you can do that calculation on your own if you really want to check, but x to the 5th is 32, this is 16, 16 times 25 is a lot bigger than 32 divided by 10, right? And this is positive, this is positive. We're adding these two together, but this one's getting subtracted. So at small values, this is far more important than this 1/10 x to the 5th. However, as x gets larger and larger, x to the 5th becomes so much greater than x to the 4th that x to the 4th becomes insignificant. For example, when x is equal to 1,000, 1/10. So despite the fact that this is being divided by 10 and this one's being multiplied by 25, this is 1/10 x to the 5th is equal to 1 times 10 to the 14th, whereas negative 25 x to the 4th is equal to negative 2.5 times 10 to the 13th. That means that this one over here is an entire degree of 10 bigger, one whole magnitude. So if we subtracted these, you'd get something like, I think it would be 7.5 times 10 to the 13th, which is, 13th, which is like 750000000. It's like that much bigger, right? And that's just when x equals 1,000. So you can imagine that when x equals 1,000,000, it gets even bigger and bigger and bigger. Because of this, if the leading coefficient is positive, the graph will end going up. And if a is negative, the graph will end going down. So basically, if you're trying to figure out what the end behavior of a graph is, all you have to do is find whatever x value has the highest exponent, and then look at the leading coefficient. Look at the A. If A is positive, end behavior is positive. If A is negative, then the end behavior is negative. You can also see that also lets you tell from graphs what the A value is. So for instance, with all of these graphs, since the end behavior is negative, I know that A is negative. Since the end behavior on this one is positive, it's going up, we know that A is positive. This one, end behavior going down, A is negative. This one, end behavior is going up, so A is positive. Right, so pretty simple. Most of the stuff in this chapter I don't think is too terribly difficult at face value, but some of it might be just a little bit confusing to see where you're supposed to look for to solve each problem. But we will have plenty of time to work together in class and talk about this stuff, so hopefully it's not too confusing right now. But that is it for this lecture, and your assignment's going to be pretty short for this one too. Most of the stuff in this one isn't particularly important, so I just wanted to go over the basic things, and then we'll move on to section 4.3. Looking ahead, I have decided that I'm not going to take any of these out, but because I'm not taking any of them out, most of them are going to be shortened a little bit. So hopefully your assignments reflect that and aren't too bad. But once again, it will be really important to stay as caught up as possible. So yeah.